everyone. Today's going to be a short talk about running self-energy binding theory in the group. How to use like the overview of like using the code and what does this set code is doing. So first of all, I will just briefly describe what is the quantum embedding method for electronic structure problem. And then I will give an overview of set that using a combination of UGF2 plus PPC set. This is the program I discussed last time, and this is another one. And I just show some input file as an example using an antiferromagnetic manganese oxide. So for set, I suppose you already have the self-consistent GW solution for whatever system you're interested in, and so that represents this blue color. And then for set, but most of the time there's still some other some missing strong correlation, especially those are local that are missed in the self-consistent GW solution. So set is a way to provide to evaluate this strong local correlation by first choosing a subset, m subset of destroying strongly correlated local orbitals defined by whatever orthogonal orbital you're interested in, and then you basically write your self-energy in terms of this GW self-energy plus the impurity self-energy, which is local, minus this double counting. And what this set is basically doing is you try to construct the Hamiltonian, the impurity Hamiltonian, to compute this sigma impurity, and then do this combine all these different components to construct the total self-energy for the entire system. So actually, last time we discussed self-consistent GW is using this Hamiltonian in the block basis. So what it's trying to do for set is, or more precisely PPC set code, is it tries to construct an impurity Hamiltonian in a localized atomic orbit basis, which or any other orthogonal basis for the impurity problem. So what it means is we try to compute this non-interacting Hamiltonian and this local Coulomb interaction and the coupling of the impurity orbitals to the bath, all these matrix elements. And all these matrix elements can be computed. For example, for this Coulomb interaction, it just comes from the local one of the parent method. And all the other terms are based on the self-consistent GW solution. So what it does is once you run the self-consistent GW solution, you try to compute the U, and from the row matrix element, and you compute the H tilde 0 epsilon B VIB from the self-consistent GW solution. So this is the overview of the material simulation if you're trying to run UGF2. And now we're adding another step here. Right after this GW calculation, we add another step, which using the PPC set to calculate the impurity Hamiltonian and the impurity self-energy. And the code is writing mostly in Python, but because you're trying to solve the impurity problem, so everything except the everything, all the impurity solver most likely is written in C++ or any other language, depends on the impurity type of impurity solver. And your input is of course, the matrix element from the PyCF, the row matrix element calculated from PyCF, but also the Green's function self-energy from the self-consistent UGF2 code. And then once you are done with this step, you can of course do the post-processing step to calculate all other physical observable. So how to build this? The code is in CQMP pp/ppc set. It depends on the CMake to build the code, and use HDF5. The one of the impurity solver, which is the most common one used in the code, is the ED lib, which for the exact ionization, and you also need the dependency on the GF mole to calculate the double cognitive sample energy. And how to build this, you simply click clone and then go to that directory and then build it. And this will build like several components, including the ED leaf and also the GF mole in principle, yeah. So how do you run this? There are several, before you run actually the main stat, which is the set underscore main.py, there are two like warm-up steps like you have to do. First one is you have to define your problem. So of course, when we say the PPC set, try to construct this Hamiltonian and then solve this Hamiltonian. So the first thing is you have to define your orbitals or define your impurity. And this is like defined by yourself as a user input. So, and then you transform the Coulomb integrals, which once you define the problem, you transform this general Coulomb interaction in the block state to this local impurity state, the basis. And then once everything is done, you can finally run the set. So the first step is like define the problem, you choose the impurity subset space A, and then you use the state underscore transform.py. And this is the example which is directly extracted onto this previous talk. And then this will generate the transformation matrices from the whole entire system to the impurity subspace, such that this will be used in all the subsequent calculation from the both general object to the impurity object. And then you have to project the Coulomb integrals for the whole system onto this local impurity subspace. This projection, and this is done in a C++ code, which will be automatically built once you follow this previous CMake steps. And this will be the output, and this is the input, which contain the transformation matrices from the last step. And then this is a long list of the basic parameters. By no means I want you to read everything. It's just like putting everything here. So like if you actually using it, you can actually maybe go back to this slide and try to have a better understanding of what each parameters is doing and which of those are actually necessary for real calculations. So you can always do this Python state underscore main.py help to check like other parameters list for the complete parameter list. And one of the several things, list 2 is the output of the previous like warm-up steps from the SEET underscore transform.py and this in transform C++ code. So these two will be generated only after you run these two warm-up steps. And for this, and all the weakly coupling solution from UGF2 is parsed through this, and all the one-body metrics and then from like the rule one-body metrics and then calculate from PySet, it parsed through this. And then wait. Okay, yeah. So the other thing is like you have to once you finally really run the set underscore the set code, you have to specify the impurity solver. Right now we have ED, but we also support other stuff like couple cluster or like other like NCA, OCA, stuff like that. So you can always check this, and then this will give you a list of the impurity solver and have the precise name to specify them. Other than basic parameters, there are some usable parameters, especially when bath filling is required. So what does that mean is I found, suppose you're running ED and you have like impurity like consists of three T2G orbitals from a transition metal. and your system is like perfect cubic. So in principle, this 3 T2G orbitals should be perfectly degenerate. But the thing is, when best fitting is involved, this degeneracy will be broken due to this error of the best fitting, and then this error, the symmetry breaking will be amplified due to the accumulated error once you start to do this consistency. So the workaround is you explicitly symmetrize all these orbitals or the spin, stuff like that. So the bottom line is, even if your input is like almost degenerate, like up to maybe up to 10 to the minus 8 difference, once you go through this best fitting procedure, the difference will be amplified, and then once you do the consistency, it will eventually break the symmetry. So you have to impose the symmetry explicitly. So for example, you have this symmetrization between spin up, spin down, and you can also use this orbital same groups to group orbital within the same impurities. For example, the 3 T2G orbitals, you can specify the 3 of them are exactly the same. So we'll do this symmetrization, and this will only work with one of these or diagonal in this impurity space. Or you can also do this underscore same underscore plot. That imagine you have this antiferrometric case. You solve the impurity problem on nickel, like antiferrometric nickel oxide. You solve the impurity problem on nickel 1. The nickel 2 is just a mirror of that, but like you flip the spin. So you can do this. You can only solve one impurity problem, and then use this argument to copy and pass to the other nickel. Yeah. So the other ED the parameters that used especially for ED, these are also should already be covered in Sergey's ED talk. So this two you have to generate. This two is the important one. Like this one is the mineralization types for different impurities. So now we have 3 types of mineralization. So the 3 different types is defined through different residues. So the type 0 is like we define the residue as a difference between the original mineralization minus the fitted one times the square root of the frequency. And so you can see different types will have different weight in different frequency points. And the final residue is like the sum over all the frequency. So you can see different type of fitting is actually in a way focus on different region of your frequency window.
John, I have a quick question here. So conceptually, solving the ED problem is one thing, and solving the set loop is another thing, and then fitting to go from continuous hybridization to discrete one is again basically an isolated step.
Mm-hmm.
So is that a different program? And is it the same program, whether you do ED or couple clusters or CI or something like that? Or it's all built in?
No, so the ED lib only take care of the compute the Hamiltonian and solve the impurity.
None of the fitting, right?
Yeah. So the fitting used for ED or couple cluster or implemented in PVC set.
Okay.
Yeah.
And so it's a part of PVC set.
Yeah.
And how difficult is it to find other fitting methods that one might want to explore? Is it well separated out, or it's basically just?
It's well separated out. It's just basically separated out into one single Python script.
Okay.
Yes. So multiplication to PVC set should be easy because everything is written.
Interface for the solver, and then you just implement this interface to your particular solver, and that's basically.
Yeah. And like everything is written in Python, so it'll be much easier to understand and do some. Yeah. So the bottom line is we have different type of mineralization for path fitting, but the thing is you never in practice you will never know which one does better. So in practice you have to, as the first trial run, you have to kind of guess, and then the output of the PVC set will output the PD, like the plot, the fitting plot this or this fitting one on top of the original, the exact hybridization, and then you have to check manually whether this is good, your choice of fitting type is good enough. And unfortunately, you have to monitor this from iteration to iteration.
So this is actually it's a major source of error and a major source of confusion. So you really have to look at these fit plots and see what they're doing. And especially if your cell consistency jumps, like, during convergence, you see that you're converging sort of somewhere and all of a sudden you end up somewhere else. That's often because the fit procedure here became unstable or just found a different local limit.
Yeah. So, and this file is the initial guess for the best fitting. So once in the first iteration, you have to provide some initial guess, and then you update all these parameters. And this turns out to be also very essential for good fitting. You have to start from a reasonable one.
If I don't have a reasonable one, how do I come up with one?
So usually we use this uniform. Usually we start from this uniform orbital arrangement, and the coupling, I guess we assume is like some constant value. Yeah, but I'm pretty sure there's could be something else, a bit more systematic or even
Yeah, the fitting it's a very technical step, but it's a very fragile step.
Yeah, that's
So it's really the Achilles heel of this entire procedure is that you have to fit that.
And all these parameters are for this purpose. So this step is very fragile, and yeah.
So I guess the conclusion is don't ever look at the final result before you look at what the hybridization fits have been doing during convergence.
Yeah. So now we're in the final step. So this is the example for using for applying set to the ferromanganic manganese oxide. So the system has four atoms. And you have two manganese atoms and two oxygen atoms. So and the zero impurity is T2G. The impurity 1 is only EG, and impurity 2 is oxygen P. So you can see I have two manganese atoms, but I only have 3 impurities. So in principle, if we want to include manganese T2G, I will imagine I will need 2, each one for each. But because of this orbital symmetry block that I specified, so I specified the impurity 0 as a T2G from this one, and then I tell the scope there is another symmetry related orbital blocks which correspond to 48, 49, 51 orbitals that actually correspond to the T2G of the another manganese atoms. And the minus sign implies that I'm gonna flip the spin for the population for the result. So yeah, so that's why I only need to calculate 1. And this is also very important because if you actually calculate like the manganese 1 T2G and manganese 2 T2G explicitly, the best fitting result will be different, even though your input is really similar. And then eventually you break the symmetry between these two as well. So you have to only solve one of them and then copy and pass to the other one.
So that's another indication that this procedure is actually super fragile.
Yeah. So, and this one, and yeah, so for the manganese EG, you would do it as well. And then for oxygen P, this is the same. But the other thing is this orbital symmetry groups. So so this is for impurity 0, impurity 1, impurity 2. So I put basically this tells within impurity, what's the like which orbitals are similar, like a symmetry related to the other one. So this zero doesn't mean anything. It's just like you have to use whatever symbol. So that means for this line, it means all the T3 orbitals are the same. They're using the same number, so they're the same. So we'll do this additional symmetrization within this mobility T2G after every steps. And the EG orbitals are also all the same. And there's two. All of this, the three lines based on the monoid oxide qubit system. So you can assume this T2G, EG, and oxygen P are exactly the same within each impurity problem. Yeah, so you pass this mean type file by using this format, and then math file. Well, I can put that, but we have another script to generate the initial fast fitting parameters. So I use present here, but it should be in the code. Yes, so yeah, so that's pretty much it. So this is a brief overview, and I probably need to cover like some like other groups of consistency like eventually, but this is basically all you need to know if you want to run the inner loops of consistency. And this is an example, in a way, complicated example, because you have this all this and like magnetic phase, the state, and then this symmetry related stuff. Yeah, so this should be applied to most of the other application.
All right, thanks. Yeah, so let's stop the recording.